Hey everyone. Today we're jumping into a puzzle that's right at the heart of modern AI. You see, for decades, the golden rule was pretty simple. If you make your model too complicated, it's going to fail. But today's best AI models are absolutely massive, and they work better than anything we've ever seen. So what's going on? How is that even possible? Let's get into it. It really all comes down to this one fundamental question. When we show a machine a bunch of data, we want it to learn the deep patterns, right? The actual signal. We don't want it to just memorize every single data point, warts and all, including all the random noise. And striking that perfect balance, well, that's the ultimate challenge.
And this challenge, it creates something we can call the learner's dilemma. You can think of every single learning algorithm as walking a kind of tightrope between two big ways it can fail.
Okay, so on one side of the tightrope, you've got underfitting. This happens when the model is just, well, it's too simple. It can't quite grasp the real patterns in the data. Think of it like this. You're studying for a big history final, but all you learn is the year the war started. You've completely missed the point. Now, on the other side, you've got overfitting. This is where the model is so complex that it memorizes the training data perfectly. It learns all the noise, the random flukes, even the typos in the textbook. It'll ace the practice questions, sure, but because it has zero real understanding, it's going to bomb the actual exam.
And this brings us to the more technical terms for these two problems. Underfitting, that's a problem of high bias. It means the model's assumptions are just too rigid and probably wrong. Overfitting, on the other hand, that's a problem of high variance. It means the model is way too sensitive. It's changing like crazy with every tiny little fluctuation in the data.
So for decades, pretty much the entire field of statistics and machine learning was built around one single idea: finding the perfect balance between this bias and variance. It was a classical balancing act.
And the bullseye analogy makes this super clear. The goal, the dream, is low bias and low variance, all your shots hitting the bullseye. High bias is like your shots are all clustered together, but in the wrong spot. You're consistently wrong. High variance, your shots are just all over the target, a total mess.
So just to lock this in, bias is the error you get from making the wrong assumptions. Your model is just too simple, and it stubbornly misses the real pattern. This is our underfitting problem.
And variance is the error you get from being way too twitchy and sensitive. The model isn't just learning the signal, it's learning all the random noise too. That's what gives you those scattered shots on the target. That's our overfitting problem. And this was the textbook solution for ages. It's the classic U-shaped curve. As your model gets more complex, the error goes down, fantastic, but only up to a point. Then it hits a sweet spot, and after that, the model starts to overfit and the error starts climbing right back up. For decades, the entire game was about stopping right at the bottom of that U. So the old rule was crystal clear. You should never, ever perfectly memorize the training data. If your model had zero error, that was the biggest red flag you could imagine. It meant your model was overfit and was absolutely doomed to fail when it saw anything new.
But then, something really strange started to happen in the world of modern AI. The models that were breaking every single record were also the ones that were completely shattering this fundamental rule.
The models we use today, like the ones that power the large language models you hear about, they are just unimaginably complex. We're talking about models that have hundreds of billions or, even over 1 trillion parameters. Now, according to that classic U-shaped curve, these things should be catastrophic failures. They should be worthless.
And yet, as this quote from a really groundbreaking 2019 paper points out, the exact opposite is true. These gigantic models are trained to get that perfect score, to have zero error, to perfectly fit the data, and they perform incredibly well. This was the paradox that everybody needed to figure out.
So, this is the central mystery we're here to solve today. How on earth can these models memorize everything and still work so well? What happened to that careful balancing act?
Well, the answer lies in a new discovery. That classical U-shaped curve, it was only showing us half the picture. It's time to look at the new, complete map of how this works.
And here it is, the double descent curve. This is the big reveal, the aha moment. You can see our old friend, the classical U-shape, right there on the left. But look what happens after the error peaks. That peak is called the interpolation threshold. It's the point where the model can finally fit the data perfectly. As you keep adding complexity past that point, the error doesn't just keep rising. It starts to go down again. It's wild.
Okay, so let's just break this down. First, you have that familiar classical regime. Your error goes down, things are good. Then it starts to go up as variance kicks in. Then you hit that interpolation threshold, where the model can finally memorize everything. That's where the error peaks. But then you enter what's called the modern, over-parameterized regime. And totally counterintuitively, as the model gets even bigger, the error starts to fall all over again.
So the most important thing to understand is this. In this new modern regime, the old rules just don't apply. It's not a trade-off anymore. Research actually shows that once you get past that interpolation peak, both bias and variance can start to decrease together as the model gets bigger.
But why? The best intuition here is to think of it as a sort of modern-day Occam's razor. Once a model is complex enough to perfectly fit the data, there isn't just one way to do it, there are infinite ways. And a massively over-parameterized model has so much flexibility that out of all those infinite perfect solutions, it can find one that is also incredibly smooth and, in a mathematical sense, simple. So a bigger model can actually find a less complex solution. It sounds like a contradiction, but it's true.
And this discovery, it fundamentally changes how we think about building and training AI. Honestly, it's the reason that today's most powerful models even work in the first place. Okay, so what are the big takeaways from all this? First, that classic U-shaped curve we all learned about? It's incomplete. It's only half the story. Second, in the wild world of modern AI, sometimes you have to push right through that overfitting peak to actually get better performance. This double descent phenomenon is the secret sauce behind today's giant neural networks. The goal has shifted. It's not about finding a delicate sweet spot anymore. It's about building a model that's big enough to find the absolute simplest of all the perfect solutions.
And this leaves us with a pretty fascinating question for the future, doesn't it? We've just watched one of the oldest rules in statistics get completely turned on its head. So, if too complex isn't always the enemy we thought it was, what other long-held assumptions are about to get challenged next? What new principles are we going to discover as we keep building the AIs of tomorrow?